We're going to cover excretion in this lecture. The amount of solute that is excreted in the urine is equal to the amount that is filtered at the glomerulus plus the amount that is secreted, which remember that's when the solute is moved from the blood into the renal tubule, minus the amount that's reabsorbed. So remember that's when the solute is moved from the filtrate in the renal tubule back into the blood. And then clearance is just the volume of plasma from which the solute is completely removed or cleared by the kidneys per unit time. So you just take the urine concentration of the solute times the volume of urine that's produced per unit time, and then divide that by the plasma concentration of the solute. I'm not going to ask you about clearance on the exam. So we're just kind of running out of time, and we'll just briefly mention what it's used for, but I'm not going to ask you about it on the exam. So clinical uses of clearance, you will see this used in medicine. It is used to estimate the glomerular filtration rate, or GFR. And why we want to know the patient's GFR is it tells us how healthy the patient's kidneys are. So how well are they working? And we can actually follow the GFR if we have a patient who was diagnosed with chronic renal failure. And as the chronic renal failure progresses, we can actually see the GFR getting lower and lower. So it'll decrease over time, and that'll give us an idea of how fast the kidneys are declining. If the GFR is less than normal, then you do need to decrease the drug dosages for the patient. And then the other use for clearance is it's used to determine if a solute is reabsorbed or secreted, which is important in pharmacology. So if a particular drug is reabsorbed, that means that you don't have to give as high of a dose of that drug. And if the drug is secreted, then that means you'll have to increase the dose of the drug that you give the patient. One way to estimate the glomerular filtration rate in patients is to measure the creatinine clearance. Remember, creatinine is a waste product that comes from creatine phosphate in the skeletal muscles. And remember, that's used to make ATP. So what we'll do is we'll take a blood sample from the patient, and you can measure the creatinine concentration in the blood. And then the patient will collect 24 hours of urine. We'll measure the volume of urine produced in 24 hours. And then we'll also measure the creatinine concentration in the urine. And so if you take those numbers and you take the urine volume, multiply that by the urine concentration of the creatinine, and then divide that by the plasma concentration of the creatinine, that'll give you a rough estimate of the glomerular filtration rate. So that's something that could be done in patients. And then the last thing I want to cover is excretion of urine. So remember, we had 3 steps to make the urine. We had filtration happening at the glomerulus, where we're going to filter the plasma to make our filtrate, and then we're going to reabsorb the things we want to save. So about 99% of the water, 100% of the glucose and other nutrients. And then we're going to secrete things like hydrogen ions for acid-base balance. And also if we had any extra waste products or drugs that didn't get filtered the first time around, we can secrete them into the urine. And then our last step after we've made the urine is to excrete it from the body. So the urine from the collecting ducts is going to drain into the renal pelvis, which will then empty into the ureters. The ureters will then empty the urine into the bladder where it will be temporarily stored. And then during urination, the urine will be excreted to the outside through the urethra. The medical term for urination is called micturition. So you could say, excuse me, I have to go micturate, and no one will know what you're doing, but you're urinating. So micturition or urination is under both involuntary control and voluntary control. So with involuntary control, we have the autonomic nervous system, and we're going to increase parasympathetic stimulation and decrease sympathetic stimulation in order to urinate. The wall of the bladder is made up of smooth muscle called the detrusor muscle. And parasympathetic stimulation will cause the detrusor muscle to contract, and that will help squeeze the urine out of the bladder. And then we also have the internal urethral sphincter. So there's a circle of smooth muscle around the urethra here. And if we decrease sympathetic stimulation to the internal urethral sphincter, that will relax and allow the urine to start going down the urethra. We do have another urethral sphincter. This is our external urethral sphincter, and this is actually made out of skeletal muscle, so that's under voluntary control. So your brain has to give you the okay that you're in an appropriate place, appropriate time to urinate, and then you can go ahead and urinate. And this is the Micturition Reflex. So there are sensory neurons in the wall of the bladder that will sense the stretch, how full the bladder is getting. It will send a signal to the spinal cord, and we will send messages up to the brain to say, hey, the bladder is feeling pretty full. We probably need to find a place to go to the bathroom. And then we're also going to stimulate the parasympathetic neurons that innervate the smooth muscle in the wall of the bladder to contract. And then we're also going to be sending messages down from the brain to the lower motor neurons that innervate the external urethral sphincter, and that will relax, and then you can urinate.